that we know what the best model is based on our random subset of data, applying that model, the spectral clustering model, to our full data set, and then running a brief analysis to interpret the outcomes of that cluster. So first and foremost, let's create our new data frame that we're going to be using for our analysis. Okay, and there we go. So this is just the data frame that we're ultimately going to be using for the analysis. We have dropped PC1 and PC2 from this. In this particular case, we will be using PC1 and PC2 for our visualizations, but we're not going to be using them for the actual analysis of the clusters. Let's go ahead and do our clustering as well. All right, so what you see here is the spectral clustering. Again, we're doing this with all of our data this time. That is to say, we're using all of the dimensions, every single variable, so count, T1, T2, humidity, wind speed. We're no longer just running this on PC1 and PC2. This will, of course, take longer to do the analysis, and we will be doing the classification across all dimensions of our data instead of the summaries of the dimensions of our data. But ultimately, the clusters we get should be more meaningful because we will be including all of the information that we have at our disposal. However, unlike up here, when we did our different clustering, in these cases, there were very, very clear delineations of our clusters. That is, there's very little overlap between the different colors in these. In this case, we will see a little bit of overlap because we're going to visualize our clusters on these PC dimensions, the different components that we created, but we're going to be calculating our clusters based on all of our data. So we should see a little bit more mixing than we have in the past. So I'm going to go ahead and run this because this will take a moment. And while this runs, I'm going to go ahead and write the code for the figure. All right, there we go. So this finally completed. So we'll go ahead and run our visualization. And here you can see the final result. So we have our three different classes still because we've still identified three clusters. But we can see there are clear classes. There are clearly defined instances in this kind of component space. However, they're not as sharply defined. There is some overlap, so you can see there's some mixture. This is more representative of the real world, where you have different hours of the day. There may be some that are very unique. So these in the lower left, where the yellow ones are, those might be nighttime or morning or something along those lines. The blue ones on the upper right might be daytime or evening or some other correlation, but they're still mixing across these. The next thing that we want to do, now that we actually have these clusters, well, at this point, you could be done. You could simply say, all I was trying to accomplish was identify what are the generic clusters within my data. In terms of clustering itself, this is the end of that pathway where you've now identified kind of the final set of clusters that one might use. However, we do want to provide at least one example of how you would use clusters in practice. So first and foremost, to do that, we actually need to build a tree to see what the predominant splits are here. So just like when we were using PC 1 and 2, it's unclear what the driving factors are behind these clusters. So we do want to examine that. So first we'll create that tree. And there we go. And I just copy and pasted the exact same visualization code we've used a few times now. So what does this tree tell us? This tree tells us the key factors that are driving our class definitions. So down here at the bottom of our tree, you can see that there are a number of different outcomes, but the key things that we need to pay attention to here are that the count, and your counts may be very slightly different depending on the nuances of your data, but it should look very, very similar to this. But the most important things are that we have different subsets where there are less busy days. So that is counts of bike rentals during an hour or less than 929.5. Those are these cases over here, and that's what's defining class 2, Y2. And then in addition, we have some busier days, some what I would call medium busy days, so more average days. They are greater than 929, but less than 2,926. And then busier days, which are greater than 2,926. And that's the key thing that is defining our classes. So what can we use this for? We now know the most important thresholds for count, given all of our other data, for helping us distinguish between different classes. We also know that count is one of the most important things distinguishing different hours in terms of our data. So we can use this to create meaningful thresholds for a secondary analysis. And so we're just going to do a quick example of that, where what I'm going to do is create a hypothetical model trying to explain what is most important in describing hours that are going to be busy, average busy, or not busy. And the way that we'll do this is by building another classification tree where we'll be trying to fit those three classes, class 1 being not very busy, class 2 being medium levels, average busy, and then class 3 being very busy. And then we will interpret the tree to try to understand what the primary drivers are. All right, briefly, I do want to walk through exactly why I defined y like this. So first and foremost, I'm defining a new x data frame. So for my covariates, where I'm just dropping PC1 and PC2 because we're not going to be using that in this analysis. PC1 and PC2 would be very difficult for us to interpret, and so would just thus not be very helpful. Then I define my classes. So first of all, class 1 is not busy. So this is going to create a binary. This part of the code right here, what's highlighted right now, will create a binary 0 or 1, where it is 0 in all cases where it is greater, count is greater than 929.5, and 1 in cases where it's less than 929.5. So I'm going to take that 1 and multiply it by 1. You obviously don't need to include that. This is just for interpretation. Class 2, I'm doing the same thing, where I'm just saying that I want the medium level to be defined by anything that is 920, actually this should be 929.5, and less than 2,926. So this is representative of our medium class of busy, and here it's just multiplied by 2. And then very busy is anything that's busier than 2926. So when I run this, this will give me, because only one of these can be true, y c1 plus c2 plus c3 will give you a 1, 2, or 3, depending on which one of these criteria was met. There's lots of different ways you could program it. This was just a shorthand way to do it. This will then be our outcome that we are interested in predicting. And now we need to do one quick thing, which is just remove count from our data frame. Because we are using count to define our three classes, we don't want to predict with count because that would not give us meaningful information. Once I do that, I'm then going to go ahead and fit the tree and print it out to the screen. So let's say that there is a new hour of a day. Let's say I'm building a real-time model that takes in what hour of the day it is and various weather characteristics about that hour, and then predicts if it will be busy or not. This is a tree that could facilitate that. So for example, if I'm looking at an hour of the day that is before 6:30 in the morning, or really just 6 in the morning, then I would be then considering if it is humid or not. And then depending on how humid it is, I would be able to identify if it's likely to be an average day or an average hour. So sometimes those are a little bit busier. Or is it going to be a low, not very busy hour? You can also see that almost every single time that you have the hour of day less than 6.5, it's not busy. So we have 45 samples in not busy here, 365 here, 4,642 here. So almost every prediction we would predict, other than one very specific humidity case where there's one example where it was an average busy, it's almost always not busy during those hours. So the model that took in the information would predict likely it's not busy. Going the other way, this is where we would start to be able to distinguish between average days and exceptionally busy days. And we would be able to say, okay, on a day where it's not hour of day 6.5, but it is less than 20.5, so it's before or equal to 8 p.m. at night, then we can look at these cases. So if it's before 8 p.m. at night and it's not a very humid day, then we would end up with this set. So it would likely be an average day. It's not very humid before 8, or an average hour. It's not very humid and it's before 8 o'clock. This, on the other hand, this would be a much more, this is a little bit different. This is a above average humidity hour. You get a little bit less pressure. It's less likely that you're going to have an average day and more likely you're going to have kind of a slightly less busy day. And you can see that the reason I'm saying that is because this number here, which indicates a below average busyness, this 1501 is bigger than the 853 here. So therefore there are more hours where there were less bike rentals in the case where the humidity was higher. which of course intuitively makes sense, but but the model itself would be able to unpack these particular trends. And then again over here for the temperature. So this is a very simple model, but a model that you could define based on your clusters, that the patterns you saw in the clusters, that would be helpful in predicting the hourly likelihood that a bike there will be a lot of bikes checked out, an average number of bikes checked out, or a relatively low number of bikes checked out. In this simple case, one could use a model like this, more refined than this, but like this, to help judge things like how many people should we hire at what hours to ensure that our bike rental locations are fully equipped.